Friends, in this lecture I would like to continue our discussion on electromagnetic wave propagation in plasma. Here we will discuss the electromagnetic wave dispersion relation, phase velocity and attenuation constant, deduce an expression for skin depth in overdense plasmas. We also study the propagation of or the flow of energy within electromagnetic wave. In absorbing media, collisional plasmas, we will calculate the power loss in decibels, and if time permits, I will discuss the reflection of electromagnetic waves at normal incidence from plasmas. The reference for today's presentation is again the same book, Electromagnetic Theory for Telecommunications by Professor C.S. Liu and myself, published by Cambridge University Press. We were discussing the plane wave solution like E is equal to A exponential minus I omega t minus k dot r. Under what condition this solution will satisfy Maxwell's equations? We considered third and fourth Maxwell's equations, and those equations on replacing del operator by I k and time derivative as minus I omega take the following form. The third Maxwell's equation takes the form k cross E is equal to omega mu 0 into h, and the fourth equation is k cross h is equal to minus omega epsilon 0 epsilon effective into E. They are coupled in E and H. So, what I did was I took k cross of the first equation and used the second one, and I got this relation k cross E is equal to minus omega square mu 0 epsilon effective into E. First of all, if I take k dot of this equation, then left hand side will be 0, because this is a vector perpendicular to k as well as k cross E. So, if I dot this equation with k, so multiply this equation by k dot, the left hand side is 0, so right hand side should also be 0, means epsilon effective into k dot E should be 0, because omega is a constant, epsilon 0 mu 0 are constant, so they cannot be 0. So, this is either this should be 0 or this should be 0. So, one simple consequence of this equation is that my solution given above will satisfy these equations only when either k dot E is 0 or epsilon effective is 0. Let us see. One possibility is that epsilon effective you make 0. In view of this, if I write down my k cross E equation again, I can write down this k cross E equation as, let me write this, I think I have been little fast here, k cross E is equal to minus omega square mu 0 epsilon 0 into epsilon effective into E. This was the basic equation whose k dot I took, and I got this condition that I can satisfy this equation and this is 0. When I put this equal to 0, what does this say? This left hand side is identically equal to k, this k, into k dot E minus E into k dot k, which is k square. And because I am choosing epsilon effective equal to 0, this should be 0. This says that this is a vector in the direction of E, this is a vector in the direction of k. These two can be equal only when E is parallel to k. So, important consequence is that E is parallel to k. And if you go to third Maxwell equation, which I had written as curl of, rather sorry, not curl, k cross E is equal to omega mu 0 h. So, if E is parallel to k, this term will be 0. So, h will be 0. This is a very important consequence. So, whenever epsilon effective is 0, those waves will have electric field parallel to the direction of propagation and will have no magnetic field. So, they cannot be called as electromagnetic waves because there is no magnetic field. They will be called as purely electric waves. In plasma jargon, they are called electrostatic waves. And if they are traveling in the direction of k, this is my direction of k vector, then the electric field of these waves will oscillate in the same direction, like this. Now, what will happen in such a case? They are called longitudinal waves, and in some region the electric field will be in this direction, at the same instant in some direction will be like this, and somewhere this will be like this. So, these electrons will be compressed somewhere, they will be rarefied somewhere. So, this gives rise to space charge oscillations or density oscillations. So, these waves are also known as density oscillations or propagating density perturbations. They are given a name, electrostatic waves. This is a very important class of waves in plasma physics. Lately, these waves have been found to be very useful in electron acceleration, and electron acceleration reaching the values of about 1 GeV have been achieved by these waves. So, for particle acceleration, these waves are very useful. Well, we shall discuss those utilities of these waves later on. Second possibility to satisfy the k dot of this equation being 0 is that k dot E is 0. If I choose k dot E equal to 0, then in this equation sorry, if I simplify, this term will be simply equal to minus k square E, because this is 0. This is the expansion of this term. So, if I choose k dot E equal to 0, this is 0, only this will survive. So, put this in place of here and equate through this, because in this case epsilon effective is non-zero. So, right hand side is not 0. So, what you get here is minus k square E is equal to minus omega square mu 0 epsilon 0 into epsilon effective into E. These waves have k given by this relation. So, I will write down k for these waves. Is equal to omega is k square is equal to omega square mu 0 epsilon 0 into epsilon effective. Let us understand the character of these waves. First of all, mu 0, epsilon 0 are what? Epsilon 0 is the free space permittivity in MKS units. Its value is 10 to the power minus 9 upon 36 pi. Mu 0 is called free space magnetic permeability, whose value is 4 pi into 10 to the power minus 7 in MKS units, both in MKS units. If I put these values, epsilon 0 mu 0 turns out to be 1 upon c square, where c is the velocity of light in free space given by 3 into 10 to the power 8 meter per second. So I will put this in here and I will get k square is equal to omega square by c square into 1 minus, for epsilon effective is omega p square upon omega square 1 plus I nu by omega. This is the dispersion relation. But how about the character of these waves, whether they are transverse or non-transverse? So let us go step by step. From fourth Maxwell equation I had written k cross h is equal to minus omega epsilon 0 epsilon effective into E. This says that E is perpendicular to k and h both, whereas from third Maxwell equation k cross E was written is equal to omega mu 0 h. So this says that h is perpendicular to k and E both. So this equation tells E is perpendicular to k. So suppose my wave is going in z direction like this, or some direction like this, suppose the direction of k, then the electric field has to be perpendicular. This will oscillate like this. Then magnetic field has to be perpendicular to both of these, like this. This is B field. So these are purely transverse waves. Electric field is perpendicular to k vector, magnetic field also perpendicular to k vector, and E and B are both perpendicular to each other. Before I proceed further, I would like to recall a quantity called Poynting vector. I will not drive this here, but I will borrow this result from a general theorem that energy flow with a wave is denoted as S, turns out to be equal to E cross H. Here real part of E has to be multiplied with the real part of H, and as we have been doing earlier, this implies that this is equal to half real part of E cross H plus E star cross H. So let me write down the values of E and H and see what is the Poynting vector. Poynting vector, well, for this Poynting vector I can write down E explicitly as A exponential minus I omega t minus k dot r. and H I just wrote down from third Maxwell equation is equal to K cross E upon omega mu 0. So what you will see here in the Poynting vector S is equal to half real part of first term is E cross H, so which is equal to E cross K cross E upon omega mu 0. The second term would be E star cross K cross E upon omega mu 0. You may note one thing in here. E has an exponential factor as exponential minus I omega t minus k dot r. This E also has. So the product, if you multiply them, will be at 2 omega frequency. Time average of this function will be 0. This is the only term whose exponential time dependence will cancel. The two factors will, because this will have minus I omega t, and if you take complex conjugate, it will give you minus I omega t, plus I omega t. So they will cancel. So time average power vector will be only, this is the term that will contribute as time average is equal to, let me write down with a different ink because this is an important expression. So this quantity is equal to 1 upon twice omega mu 0, and real part of this quantity I will write down this as vector triple product as K vector here into E dot E star minus this E vector and K dot E star. But we have already seen K dot E is equal to 0. So this term vanishes because they are transverse waves, K is perpendicular to E. So this is the only term, and you know E star is a real quantity. So this equation simply gives you time average Poynting vector simply as S average is equal to modulus of E square upon twice omega mu 0 into real part of K. If K is complex, only real part of K has to be written there. This is a very important result. If somehow we find that K is imaginary, purely imaginary, then there is no power flow because time average Poynting factor or energy flow is 0. The magnitude of this quantity is also called intensity of the wave or intensity of radiation. So let me write down this intensity of radiation as S average magnitude, which is equal to modulus of E square upon twice omega mu 0 into K real part Kr. Well, when we discuss different cases of wave propagation in different kind of plasmas, we will make use of this expression. So let me consider the wave propagation in a collisionless plasma. Where collisions are small, what you get? K square is equal to omega square by C square 1 minus omega p square over omega square. this can also be written as omega square is equal to omega p square plus k square c square. If I want k to be real, then k square should be positive. So, if I want my wave to carry energy, then omega must be bigger than omega p. That is a very important condition. Plasma does not allow the propagation of all sorts of waves. It will allow propagation of only those waves whose frequency is bigger than omega p. And if omega somehow is less than omega p, then k will be purely imaginary, and from that point on energy should be reflected back. Sometimes you have plasmas, suppose the plasma starts from here, but the density is low here and density increases in the plasma. Suppose density increases like this. If you are launching an electromagnetic wave on a plasma whose frequency is constant, but plasma frequency increases, then it will go up to a region where omega p becomes equal to omega, and beyond this omega p is bigger than omega, the wave will not propagate, it will come back. So, this is a very important phenomenon called total reflection of electromagnetic wave from critical density plasmas or from critical layer, which has been used in measuring the density profile of the ionosphere. I shall discuss this when I discuss the applications of these waves in either today or in my next talk. But let me mention something about this, that I can plot a dispersion relation omega versus k, and this will be of this form. Omega normally is plotted on the y-axis and k on the x-axis. It starts from omega p here, because waves of frequency less than omega do not propagate. So, k is not real for them, and this will go like this, and asymptotically this dispersion relation approaches a line called omega equal to kc line, called light line. And we can define a quantity called refractive index. The refractive index is defined as velocity of light in the medium in free space to velocity of light in the medium. But we know Vp is already omega by k, so this is c upon omega upon k, or kc by omega, and if I put the value of k, it turns out to be equal to 1 minus omega p square upon omega square under root. So, this quantity is less than 1 for omega bigger than omega p, and it is imaginary, which has no meaning, for omega less than omega p. So, we should not talk in terms of, because phase velocity actually does not have any meaning there. So, let me introduce a term called skin depth to characterize the penetration of fields in a overdense plasma. A plasma where omega p is bigger than omega is called overdense plasma, and a plasma where omega p is less than omega is called underdense plasma. So, in an overdense plasma, where I am choosing omega p bigger than omega, what is my k? K is equal to omega square, omega by c into 1 minus omega p square by omega square to the power half. So, k is purely imaginary. I can call this is equal to I times alpha, where alpha I will call as omega by c into omega p square by omega square minus 1 to the power half. If I put k is equal to I alpha in my electric field expression, what do I get? But k is a vector quantity, I am little worried. So, to appreciate the physical consequence of k being imaginary, I will consider the wave propagation one dimension. For 1D wave propagation, what I am going to do? I will write down, say, electric field is equal to A exponential minus I omega t minus kz. Let my wave be travelling in the z direction. This is my k vector, or a wave is going in this direction, say z axis. Space variation is always z, but k is imaginary. If I put k is equal to I alpha here, this equation can be written as E is equal to A e to the power minus alpha z exponential minus I omega t. So, in an overdense plasma, phase term does not have any z dependence, no z dependence in phase, and this entire thing is called amplitude then. And amplitude will fall off with z exponentially. Alpha has the dimension of 1 upon length, and I introduce a quantity called skin depth, which is equal to delta, and this is 1 upon alpha by definition. And if I put the value here of alpha from the previous expression, it is c upon omega p square minus omega square under root. Well, this is in the limit when there are no collisions. I consider collisionless skin depth. When the collision frequency was taken to be 0. However, if nu is included, what happens? Let us see. So, when collisions are finite, what do you expect? Your k is equal to omega by c 1 minus omega p square upon omega square 1 plus I nu by omega to the power half. For propagation of waves of frequency omega p, in a plasma, nu is always less than omega p, indeed much smaller than omega p in all plasmas. Nu is always less than omega p, and we have learned that if you want the wave to travel in a plasma with very little attenuation, omega should be bigger than omega p. So, in the limit when nu is much less than omega, you can simplify this expression. I can write down k is equal to k real plus I times k imaginary. Imaginary part comes because of this nu term. Simplify this, you get k real nearly equal to omega by c into 1 minus omega p square by omega square to the power half, and imaginary part of K is Ki of the order of, if you simplify this expression, it becomes nu upon 2c into omega p square over omega a square divided by Kr. Well, it's not K, this is 1 minus omega p square by omega square to the power half. This sort of expression you will get. You may check here that nu, if you increase a plasma with high collisionality, will give you higher value of K imaginary, and imaginary part of K always gives rise to damping of the wave. It's also called damping coefficient or attenuation constant, and in the vicinity of omega equal to omega p, this term is most dominant. So when wave goes from a low density plasma into high density plasma, two things happen. Collision frequency increases because this depends on plasma density, and because of this omega being closer to omega p now, denominator becomes smaller and there is enhancement because of that also. So this Ki is very strongly increasing function with plasma density. So if you are launching a wave into a inhomogeneous plasma whose density, suppose a plasma has a density variation like this, density is 0 here, suppose that plasma density is increasing like this, you are launching a wave. What will happen? Initially collision frequency will be very tiny. I am talking of strongly ionized plasma where collision frequency depends on electron density or ion density. So as the density increases, nu will increase, omega p will increase, this factor will decrease, and there is a considerable enhancement in Ki. So the wave gets very, very strongly damped as it travels deeper and deeper into a denser plasma. So that is the message contained in this expression. Another thing that you may note here, that if I am talking of very low frequency response at omega much less than nu, what will happen? These are the kind of waves that are of interest in the ELF range, because the frequency of ELF waves is less than collision frequency. So what will happen? In this case, K square is equal to omega a square by C square 1 minus omega p square over omega square into 1 plus I nu upon omega. What I have to do? I am choosing nu much bigger than omega, I can ignore this one, and this becomes of the order of omega square by C square into omega p square upon omega nu into I. I have ignored 1 as compared to this term because this term becomes very large when omega is very small. So this is the typical thing, and Ki becomes of the order of, take the under root, it becomes omega p by C into omega upon nu to the power half, and this I will give you 1 plus I upon root 2. This is the under root of iota I. So K has a real part and imaginary part of equal magnitude. I can write this is equal to K real plus I times K imaginary of the same value, and skin depth in this case is defined as 1 upon Ki, imaginary part of K, that will be equal to reverse of this, So C upon omega p into twice nu upon omega to the power half. The important thing is the dependence of this skin depth on frequency. This skin depth decreases with frequency. So this goes as omega to the minus half. Please note, at omega much bigger than nu, we found that the skin depth was like C upon omega p kind of thing, whereas this is like this here. So if I plot a graph of skin depth versus frequency, delta versus omega, at very low omega this will be large, and as omega approaches omega p, again this will be large. This is actually this is logarithmic plots kind of thing. So this is skin depth could be quite large at very low frequencies, like if you are sending a wave of radio frequency like 10 megahertz in a solid or in a high density plasma. In that case, skin depth could be quite large in several centimeters, whereas the same metal at microwave frequencies will have a very tiny skin depth, maybe of the order of a few microns. So skin depth is a very strong function of frequency. I think I would like to mention a quantity, because when we talk of absorption of waves via collisions, we always talk in terms of power loss in decibels. So let me introduce this quantity here. Whenever k is complex, k magnitude wise is equal to k real plus I times ki, your electric field can be written as E is equal to A amplitude exponential minus kiz for wave propagation along z axis exponential minus I omega t minus kr into z. This sort of expression you get. And as I just told you, that the Poynting vector or intensity of radiation, which is time average Poynting vector, is equal to modulus of E square divided by twice mu 0 omega into k real. This is the expression I had given to you. So if I put the values, please note here, when I take the modulus square, only a square will not come. Exponential factor was also real, and square of this will also come. So what you get, your intensity will depend on z now because of this factor, and the result would be that I can write down my intensity as this will be a square exponential minus twice ki into z upon twice mu 0 omega multiplied by kr, which is omega by c into 1 minus omega p square by omega square to the power half. This is a typical expression in a weakly collisional plasma, where I have assumed omega bigger than nu. Well, all these factors are constant in a plasma of uniform density, only this is z dependent, so I can write down this is equal to some constant I0 exponential minus twice kiz. means the amplitude intensity of radiation decreases with Z. Power loss in decibel is defined like this. As alpha, which is equal to 10 log to the base 10 of I0 upon I. And if you evaluate this quantity like this, it becomes 20 into Ki into Z into log to the base 10 of log of E. Log of E is to the base 10 is 1 upon 2.3. So, if you divide this by 2.3, this will be something like 8 point something, 8.7 or something, 8.7 I guess, into Ki into Z. So, in many experiments you measure the power loss in decibels over a certain distance Z, and hence Ki can be calculated. I will give you an example. I will give an example. A wave suffers, say, 3 dB power loss in a distance of, say, 2 meter. Estimate Ki. What should I do? It's very trivial. Alpha is 3 here. So, expression was alpha is equal to 8.7 multiplied by Ki into Z. Z is 2. So, Ki turns out to be equal to alpha is equal to 3 upon 8.7 multiplied by Z, which is 2. One can evaluate this quantity, which is I think is equal to point. This is I think 0.17 or so. You can just this is just a very rough I have written, and one can estimate. So, it's a simple calculation. The advantage here is that once you measure the power loss in decibels, you can calculate Ki, and Ki, if you put the expression for Ki, from there you can deduce the collision frequency. So, absorption measurement gives you information about the collision frequency if you know plasma density, that you can measure by some other method, and hence this is a important diagnostic technique also. I must also mention that when we were discussing the conductivity of a collisional plasma, RF conductivity of a collisional plasma, we found that heating of the medium takes place only when collisions are there, and here we have noted that damping of the wave takes place when Ki is finite or collision frequency is finite. So, collisions are responsible for both damping of the wave and heating of the plasma. After all, where the energy goes when the electromagnetic wave travels in a plasma, and if it is attenuated by the electrons, which oscillate in the presence of the electric field of the wave and which undergo oscillations, but when they collide with scatterers like ions or neutral atoms, then their velocity has a component in phase with the electric field, and that gives rise to net power dissipation. So, electrons are heated, and obviously when electrons collide with ions or neutral atoms, they impart part of their energy to those species, and they can also be heated, but the temperature of electrons in such plasmas is always bigger than the ion temperature or neutral temperature. So, I think these are some basic characteristics of electromagnetic wave propagation in plasmas. I would like to finally discuss the implication of complex K on wave reflection, because we have just learnt that if wave is launched onto a overdense plasma, then propagation constant is purely imaginary, and hence time average Poynting vector is 0. The question arises, is there some electric field still in the overdense plasma or not? So, to address this problem, I would like to discuss the problem of wave reflection from a plasma boundary. Consider a boundary between a plasma here and free space there. Plasma is characterized by a single quantity called epsilon effective, and free space has this permittivity equal to unity, it is a free space. What we do? We are launching an electromagnetic wave here. Partly the wave will be transmitted in the plasma, partly it will be reflected. So, there are three waves: a incident wave, a reflected wave, and a transmitted wave. And let me consider this direction as z direction and thus interface as z equal to 0. So, the incident wave, if I write E incident is equal to, let me take this wave is polarized perpendicular to the direction of propagation. So, either Ex is finite or Y is finite, or both can be finite, but without any loss of generality I will choose this to be X polarized, and let the amplitude of this incident wave is A0, and this is a wave travelling in the positive z direction. So, I will write down this is equal to minus I omega t minus in free space, where this is effective permittivity is 1, I can write down the propagation constant as omega by c. And similarly, reflected wave will also have A0. Suppose the amplitude is reduced by a factor Ra. A subscript means amplitude reflection coefficient. The frequency would be the same, but the direction of propagation is reversed. So, I will write down plus omega by c z. This is a reflected wave, and the transmitted would be E t. Again, it should have same polarization to satisfy the boundary conditions. Let the amplitude will be A0 into t transmitted amplitude of Ta exponential minus I omega t. The wave will have a different k vector here. Suppose is k z, where k is omega by c epsilon effective to the power half. So, now I know the fields, I must apply the continuity conditions. Well, there are two unknowns here, Ra and Ta. I require two boundary conditions. One boundary condition is that the tangential component of electric field must vanish here, must be equal on both sides, should be continuous, and second, tangential component of magnetic field should also be continuous. So, let me apply these two boundary conditions. The first boundary condition, continuity of E tangential Ex at boundary which is z equal to 0. In these expressions put z equal to 0, and so on the left hand side the field is EI, incident field, plus reflected field, x component of this, x component of this should be equal to x component transmitted field at z equal to 0. So this gives me 1 plus RA is equal to TA. Second thing is magnetic field, continuity of magnetic field. Now magnetic field we already know for a wave, B is equal to K cross E upon omega. What you get from here for the incident wave, B, well, please understand, K is in the Z direction, E is in the X direction, so K cross E will be in the Y direction. So I will write down simply By is equal to, for the incident wave this would be K is omega by C, so this will be 1 upon C A0 exponential minus I omega t minus omega by C into Z. This is the incident. So let me call this as I. By of the reflected wave I can write down similarly as minus 1 by C, because K reverses sign, into A0 exponential minus I omega t minus omega by C into Z, and By of the transmitted wave would be this R also there, I forgot RA. This will be K upon omega into A0 into TA exponential minus I omega t minus omega by Cz. Just I have used this expression to write the fields due to 3 waves in 3 different forms. Apply from there, you can write down the H, which is equal to B upon mu 0, and the continuity condition is that Hy due to the incident wave plus Hy due to the reflected wave should be Hy due to the transmitted wave. Apply this at z equal to 0. The condition turns out to be 1 minus Ra is equal to Ck upon omega into Ta. The other equation was 1 plus Ra is equal to Ta. These 2 equations can be added to obtain amplitude transmission coefficient, which is equal to 2 upon 1 plus eta, where eta is equal to Ck upon omega, or the refractive index. And similarly, amplitude reflection coefficient is 1 minus eta upon 1 plus eta. So you get amplitude reflection coefficient to be positive because eta is less than 1. So for omega bigger than omega p, if collisions are weak, then eta is nearly real and Ra is less than 1 but positive. There is no phase change on reflection. On the other hand, so no phase change on reflection. On reflection. On the other hand, if omega is less than omega p, in that case eta is imaginary, when eta is imaginary, Ra can be, this can be written as, suppose, I alpha prime, for instance, that becomes 1 minus I alpha prime upon 1 plus I alpha prime. So, modulus of this quantity will be 1. Take modulus, which is 1 plus alpha prime square under root. Denominator will also have the same magnitude, they will be unity. So, there is 100% reflection, but there is a phase change on reflection. Well, we shall elaborate on these issues later. Another important issue is that in this case T is non-zero, amplitude transmission coefficient is 2 upon 1 plus eta. If eta I put I alpha, it becomes 2 upon 1 plus I alpha prime, which is non-zero. Means if I have a plasma over dense which is omega p bigger than omega, a wave is coming in here, wave will be reflected back from there. There is no power transmission because k is imaginary there, but field is not 0. There is always a field in this region, and that is called evanescent field. So, evanescent field exists here. And how much is the evanescent field? Let me write down this expression. In terms of TA, I will write down my transmitted field is ET, x direction was the direction of polarization, amplitude was A into TA, TA I have taken as 2 upon 1 plus alpha prime, and in the second medium this goes as exponential minus omega by c into alpha prime, this is the value of k imaginary, into exponential of minus I omega t. So, your wave into z also there is having an amplitude which is decaying with z. So, if you are the boundary here, if I plot magnitude of this quantity which is called amplitude of the wave, this is I alpha, actually I is there. So, if I plot here say modulus of Et as a function of z, because of this factor it will fall down. So, this is a wave whose real part of k is 0. So, S average is 0 in the transmitted medium. I am talking about the steady state, and eventually, so there is no power transfer over there if there is no collision. I think further details of such situations we will discuss when we consider specific cases. That is all for today. Thank you.